Today we're going to look at reciprocal trig functions. So we're starting by revisiting some Year 12 questions. Okay, here come the answers. If you'd like some details about how these answers were found, you can look at the video from the PowerPoint. Let's just clarify our notation, so just a reminder. So we can simplify this by writing sine squared theta. It means the same as sine theta in brackets squared. When we add two trig functions together, if they match perfectly, then we've got two of them, just like with algebra. If we have different trig functions, we don't have a way of simplifying that one. This time we have the same trig functions, but we've got different input, so we can't simplify these. We have the same trig function, we've got different input, but this time we're multiplying. So remember, with algebra you can stick those together. You cannot mess with the two different inputs. Okay, you've got to treat that carefully. If you'd like to know more about where your trig comes from or how it was developed over the centuries, you could use one of the links from the PowerPoint. You first met trig in GCSE, and we used it for similar triangles. So all triangles that have got the same angles inside them, they might be a different way up, or they could be a different size, but the angles inside are all matching. Then we call them similar triangles, and they will have the same ratios of one side to another side. And this is a useful thing for solving lots of different problems. Okay. So we decided, because it was convenient, to name the different ratios, so we know which one we're talking about and we can use it for problem solving. So we named, if you take the adjacent side to the angle that you've selected, over the hypotenuse of a right angled triangle, we called that cosine, and so on with sine and tangent. Okay, but we could have used, there are three other different ratios we could have used. We could have done hypotenuse over adjacent, and so on. And in fact, those three do have names. So we have hypotenuse over adjacent is called secant. Hypotenuse over opposite angle side is cosecant, and adjacent over opposite is cotangent. So those are the reciprocals to adjacent over hypotenuse, and so on. So these are called the reciprocal trig functions, and as usual we shorten them because we can't be bothered to write them all out. You may see cosec as written as CSC in some books, so it's just three letters. But we usually use cosec for your course and for your textbook. Okay. Now it's really important to notice that these are reciprocals of our familiar trig functions. They are not written as something to the power of -1 and then the x, because we use that instead, as you know from looking at your calculator, for your inverse functions. So be careful not to mix those up. Let's just clarify that. Okay, so looking here, which one is the odd one out? Well, hopefully you realise they're all the same as sine squared theta except for the sine 2 theta. Similarly, we've got lots of sine cubed thetas except for 3 sine theta. Here, let's just have a look. Cosec is the same as 1 over sine. Okay. So these all match except for sine to the -1, because we call that the inverse sine function. If you know what the ratio is and you're trying to find the angle, use the inverse sine. But cosec is the same as 1 over sine, which is theta, which is sine theta to the power of -1. So that means in our notation, the sine to the -1 theta does not mean the power, but it does if it is, for example, sine cubed theta. That does mean the power of 3. So it's a little bit confusing, which is a bit annoying, but we try our best. Okay, let's just look back at these again. Now, an easy way to remember which trig function is a reciprocal of which is to look at the third letter on the new ones of secant, cosecant, and cotangent. So if you look at, let's see, if you look at the third letter of sec or secant, the third letter is C, which is the initial of cos. So sec is the reciprocal of cos. If you look at the third letter of cosec, that's S, which is the initial for sine. So that means that cosec, or that reminds you that cosec is the reciprocal of sine. And same for cotangent. The third letter is T, and that reminds you it is the reciprocal function for tan. Okay. Now, annoyingly, your calculators don't have, even on the options, function keys for sec, cosec, and cotangent, so you just have to remember it's 1 over and use your calculator for that. So we're going to have a little look at, just turn that off, we're going to have a look at an example. So I'm going to just switch to looking at my calculator here. Alright, so let's look at finding sec of 40. Okay, now we know that sec, the third letter is C, so this is 1 over cos 40. So I just go to my calculator and I'm going to make sure that I'm working with degrees. So I want shift set up. There we go. Oh no, I'm not. So I want to choose degrees for my angle, and then I can do 1 over cos 40. And that gives me, to 3 significant figures, I'll put 1.31. Okay, let's look at the next one. We've got cosec of pi over 5. Now, we'll be working with radians for this one. So let's change in setup again. I go down to the angle, change it to radians. Okay, and we go 1 over. Now, the third letter is S, so cosec is 1 over sine of pi over 5. So let's put that in. So we've got 1 over sine, and then I'm going to have pi over 5. Okay, and that gives us 1.70 to 3 significant figures. Cot of 250. So we know that cot, the third letter is T, so that's the same as 1 over tan of 250 degrees. So here we go, 1 over tan. Now, I think I'm still in radians, so let me change back to degrees. Okay, and so I can now put in 250, and there we go. We get 0.364 to 3 significant figures. Okay, right. For the next question, we've got, given that tan pi over 6 is 1 over root 3, we then have to determine the exact value of cot 5 pi over 6. Now, determine would suggest that we have to show some detail in our working here. Okay, so tan of pi over 6 is 1 over root 3, and we want cot. I know that cot of 5 pi over 6 is 1 over, third letter is T, tan 5 pi over 6. Now that 5 pi over 6 is going to be related to pi over 6, and I need to figure out how. So my favourite method is using a cast diagram, but we'll look at a graph as well. So here we go for a cast diagram. I know that tan of pi over 6 is 1 over root 3, so I'm going to try and relate my 5 pi over 6 to pi over 6. Let's find out where 5 pi over 6 is. So starting from the positive x-axis, we go anti-clockwise for positive. We know that 0 degrees is on the line. We get up to pi over 2, which would be 3 pi over 6. We keep going. If we kept going to this other side of the x-axis, that would be a full pi, 6 pi over 6. So we know that 5 pi over 6 is going to lie in this quadrant, and the spare bit here is going to be pi over 6, which is great. So the angle made with the x-axis is pi over 6. Now, in this quadrant, only sine is positive, okay? And tan is going to be negative. Okay, it will have the same value as tan pi over 6, but we'll have a negative one. So tan 5 pi over 6 is negative tan pi over 6. Okay, so that means we want the negative reciprocal of 1 over root 3, and so that will be negative root 3. Okay, right, if you're a graph person, instead of a cast person, we'd have to do a little sketch, okay, of tan. All right, I know that this is pi over 2, and this is pi. So we've worked out that 5 pi over 6 is going to be about here. And we know, so that's 5 pi over 6. But we also know that this gap, okay, is pi over 6. So if I do this equivalent gap over here, pi over 6, I know that our tans are going to have the same value, but we can see that one of them's positive, one of them's negative. So tan 5 pi over 6 is equal to negative of tan pi over 6. And so we can work it out from there. And the other marvellous thing on your calculator is that, hopefully, it can work it out exactly. So let's try it. So we've got 1 over tan of, and we want 5 pi over 6. Now, I was working in degrees, so I'm going to change it back into radians. Okay, and execute, negative root 3. So your calculators are great because they can work with exact values, but some calculators, or the older calculators, wouldn't, and you'd have had to do it by hand. But it's brilliant that you're able to check. Okay. Switching back to the questions then. So I'll just zoom through that. There we go. Here's some for you to practice. Now, if you want to think a little bit harder and deeper about what's going on, then as you go along, do one question at a time, and as you go along, think about, can I predict what my next answer would be based on what I've just done? Is there a connection there? Will that help me? And that helps you think quite mathematically about connections between different trig functions. Okay, you can check it by doing your answer properly, and then if you've got it right, brilliant. Can you explain why there's a connection there? Or if you haven't got it right, do you now understand what's happened? Why was there a connection? Here are the answers. Okay. Another set of questions to try. So this time just working in radians, but it's the same idea. There's a few unusual ones there near the bottom. Here are the solutions. Okay, so we can't always find values for some of these reciprocal functions. Okay, we're going to look in more detail about that next on the next session. Okay, and here's a couple of challenge questions. You can have a look at the video link from the PowerPoint if you'd like to for these. Right, so this is a classic exam style question. The examiners seem to really enjoy these ones. They crop up a lot. So we're given one trig function, and you have to work out the value of a different trig function. Okay. So I'm just going to show you on my calculator how this works. Right then. So we have got that cot theta is negative 8/15, and we know we're working in radians. So remember, theta is an element between 3 pi over 2 and pi over 2. So it's giving us a range of values. We have to find the exact value of sine theta and sec squared theta. An exact value must be a fraction, it must be a surd, it's not allowed to be a decimal. Okay, right, now you might just want to try on your calculator, so let's try this. So cot theta is negative 8/15, so that means, looking at the third letter, we know that tan theta would be negative 15/8. Okay, so if we do inverse tan of negative 15 over 8. Okay, it gives us in radians. And then we want to sine it. So sine of that answer gives us a decimal. So sadly, your calculator, while it will give you roughly where you should be, you cannot use it and just do inverse cot and then sine it. So we need a different strategy. And the easiest thing to do, which is similar to what we did in year 12, is draw a little right-angled triangle. So for part 1, we're going to have a right-angled triangle and use the information we've been given. Okay, I'm going to pick an angle to be theta, and I'm going to use this information. Now I know that tan is opposite over adjacent. I'm going to ignore the sign at the minute. Okay, so that means my opposite side is 15, my adjacent side is 8. I can then use Pythagoras to work out the other one. Let me see. So 8 squared plus 15 squared and then square root. The answer gives us 17. So the third side is 17. Brilliant. Right. Now then, that then tells me to get my hypotenuse, I know that would be opposite over hypotenuse, which would be 15 over 17. However, tan was negative, okay, because cot was negative. So let's have a look in our cast diagram, because the cast diagram is where we find out what's positive and what's negative. Okay. If we know that tan is negative, okay, then it's going to be where we don't see a t. We know they're all positive here. Tan is positive there, but tan is going to be negative in this quadrant and this quadrant. And in fact, the question told us to focus on the values of theta between 3 pi over 2 and 2 pi. So we start at 0, we go to pi over 2, pi, 3 pi over 2, and 2 pi. So we know that we're working in this fourth quadrant here for our angle. Okay, in that fourth quadrant, tan is negative. Brill. We need to know what sine. Well, this isn't an S, this is a C for cos, so we know that sine is also negative in that quadrant, because only cos is positive. So we need to put negative 15 over 17. Okay, so we've got that there. And in fact, from our calculator, we got negative 0.882. So if I do negative 15 over 17, hopefully we get something similar. There we go, we get the same value. Super. Right, let's look at part 2. So in part 2, we can still use that same triangle. Now we're using sec. Okay, so sec, if you remember, is 1 over cos theta. Okay, and we know that cos is adjacent over hypotenuse, so this will be hypotenuse over adjacent. Okay, and in fact we want sec squared, so I'm just going to square everything. Okay, and that means we don't have to worry about the sign, because squareds are always positive. So we've got our hypotenuse is 17 and our adjacent side is 8. Okay, so we've got 17 squared. Oh, going to make my, hopefully get my calculator to do that. 17 squared is 289, and I know that 8 squared is 64. Well done me. Okay, and there we've got our solution. All right. Now the second part of this worked example, we have it slightly different this time. Given that cosec is negative 7 over 6 and tan is positive, find cos. So we're not given the range of values for our theta, okay, but we are given some information about the sine of tan. So we start the same. We think, right, cosec, so cosec theta is 1 over sine theta. Okay, so that means sine theta would be negative 6/7. So I'm going to draw that in a triangle. Okay, I'm going to pick an angle to be theta. I know that sine is opposite over hypotenuse, so I'm going to pick my opposite side is 6 and my hypotenuse is 7. Okay, that means I can work out my other side by using Pythagoras. So I'm going to do 49 take away 36, gives us 13. So this one's going to be root 13. for our adjacent side. Okay, we're aiming to find cos, and we know that cos is adjacent over hypotenuse, and that means we will have root 13 over 7. But we don't know if we've got positive or negative yet. And we're going to use the information in the question and a lovely cast diagram to help. Okay, right. So we know that cosec, which is one over sine, is negative. Okay, so where is sine negative? So sine is positive with the all and positive with the s, so it's negative here and here, okay, where there's no mention of sine. But we also know that tan is positive. So where's tan positive? Well, tan is positive in the all section and the t section for tan. So the overlapping part there is down here. So we know that the angle we're interested in is going to be right the way around there, but we just need to know, is cos positive or negative? And in this region it's not a C, so cos is negative. So we have got negative root 13 over 7. Okay. You can also use graphs to work out which region you're talking about with positives and negatives, but you would have to look at the sine graph where that's positive. So let's have a quick look. Alright, so we can see that the sine graph is positive from 0 up to, if we're working in radians pi or degrees, 180. And we'd have to look at the tan graph. Trying to line those up. Okay, and we can see that the tan graph is positive here and here. Okay, so we want the region where both tan is positive and sine is negative, so we can see it's this region here. And finally, you would also need to look at your cos graph. So remember your cos graph. Okay, and we extend those lines down to this region. Okay, and we can see that in this zone we've got a negative value for cos. Okay. Right, let's switch back to the questions now. Okay. Just quickly flicking through that so you can go through the PowerPoint more slowly if you want to see. So here's some practice questions for you along the lines of the first part of the worked example and then the second part of the worked example. Again, if you can spot some similarities between or differences between the two questions, what's changed? How's that going to affect your answer? It helps you think more carefully about how these processes work. Okay, you can check it by doing it properly, and then maybe that will help you clarify in your head how it all works. Okay, here are the answers. There we go. Does it matter for these questions if we're working in radians or degrees? And the answer is no, because we don't have to find the angle. The only time it does help is for the earlier questions when they either give you the range of values for theta in degrees or in radians. But it doesn't really matter because we're just dealing with the ratios rather than the angles themselves. Okay, here are some exam questions to give you more of a challenge. And again, there will be a link to a video going through these step by step. These are definitely more challenging than the earlier questions. Okay, and those are the mark schemes. So, well done, and see you for the next set.